Hello everyone. So we'll see some question that is from group theory section. So these are some question we'll see here. So okay, first of all let me crop the first question. Okay. Okay, so this is the first question. So what the question says. Okay, suppose that G is a finite abelian group of order n and m is a positive integer uh, such that GCD of nm is equals to 1, then we have to prove that the map f from G to G such that f of G to the power f of G equals to G to the power m is an automorphism. Okay, so how do we approach it? Okay, so come back to the solution. So we have given that G is a finite abelian group. Finite abelian group. Okay, and GCD of nm equals to 1, where n equals to order of G, and we have given a map f from G to G, which is defined as G goes to G to the power m. We have to show that f is automorphism. So for this we have to show f is homomorphism and f is bijective. All right, so f is homomorphism. F is homomorphism. Okay, let G1 and G2 belongs to G, then f of G1 G2, which is G1 G2 to the power m, and which can be further written as G1 to the power m G2 to the power m. Why? How can we write? Since G is abelian. Okay, and this is nothing but f of G1 f of G2. Therefore f is homomorphism. Okay, now we have to show that f is bijective. Yeah, so since f is a map from G to G and G is finite. Okay, so it is enough to prove that f is 1 because there is an equivalent statement. If a map from a finite group to finite group, and if it is 1 that if it is 1 then it is on 2. Okay, yeah, so it is enough to prove that f is 1. Okay, so let f of G1 equals to f of G2, and which is G1 to the power m equals to G2 to the power m. Okay, and yeah, okay, we have given in question. Now since GCD nm equals to 1, so we can get from here that for some xy. Okay, so now it can be further written as yeah, G1 my G2 my, and we can write it as okay, yeah, and okay, okay, fine. So we get G1 equals to G2. How? We get G1 equals to G2, and hence F is 1 1 and F is 1 2, since order of G is finite, and this is the proof. Okay, now we'll see the next question. Okay, that is this one. Okay, okay, so the question says, is there a non-trivial group homomorphism from Z24 onto Z6 direction Z2? Okay, so solution, how do we approach it? Okay, so actually there does not exist, right? So how can you prove it? We'll prove it by contradiction. Okay, suppose F is a group homomorphism from Z24 onto Z6 Z2. Okay, then since it is a group onto group homomorphism, so by fundamental theorem we can write, by fundamental theorem of group homomorphism we can write Z24 by kernel of F, which is isomorphic to Z6 direction Z2. Okay, which is a contradiction. Why contradiction? Okay, so for this we need a theorem. Actually the theorem is yeah, so just I cite it here. Result. Okay, let me explain it clearly. Okay, if D is cyclic, okay, say if D is any group that is finite and which is cyclic, okay, and say F is an homomorphism, okay, then homomorphic image of D is cyclic. Okay, in particular if G is cyclic and D is normal in G, then the quotient group, that is G by D, is cyclic. Okay, so this is the result we'll use here. Okay, so basically if F is an homomorphism and D is a cyclic group, and we know that homomorphic image of a cyclic group is cyclic, and in particular if G is cyclic and D is normal in G, then the quotient group G by D is cyclic. Okay, so we'll use this result here. We have here Z24 by curve phi isomorphic to Z6 direction. Okay, Z2. All right. We know that curve phi is a normal subgroup. We know curve phi is a normal subgroup, and Z24, sorry, not 4, 24 is cyclic. So by above theorem, Z24 by curve phi is cyclic, but Z6 Z2 is not cyclic. Why? Because GCD of 6, 2 not equal to 1. So not isomorphic to Z6 Z2, so which is a contradiction, and it is the proof. So there does not exist any non-trivial group homomorphism from this to this. Okay, now we'll see the next question. Yeah, so let me drop it first. Okay, yeah, so this is the next question. So question says let 5A group homomorphism from G onto H, and suppose that H contains a normal subgroup K such that index of this is n, and we have to prove that G has a normal subgroup D such that this. Okay, fine. So come back to the solution. Okay, so how do you approach it? Okay, we have given F a homomorphism from G to H, which is onto homomorphism. Fine. And we given that H contains a normal subgroup, that is K. Okay, fine. H contains a normal subgroup, that is K. That means the quotient group H by K makes sense. Okay, this is makes sense. Okay, fine. Okay, if you define say MF, that is say alpha, from H to H by K, that is the quotient group. Okay, and say it is defined like f of H equals to HK, that is this, sorry. Okay, then alpha is a group homomorphism from H onto HK. Verifying this. Okay, this is true. Verify this. And we have given that phi from G to H onto homomorphism. We know that composition of true group homomorphism is a group homomorphism. So alpha composition phi is also a group homomorphism from G onto H by K. Okay, so by fundamental theorem of group homomorphism, we can write G kernel of this, which is isomorphic to H by K. Okay, and since we have given n equals to this, which is nothing but you can write for since both H and R are finite. Okay, so yeah, so we conclude that order of this equals to order of this equals to okay, which is nothing but n. Why? Because these are isomorphic. Okay, now let D equals to kernel of alpha combination this, then and this normal, since we know that kernel is a normal subgroup. Of G, and this is the proof. Okay, so this is the proof. Now we'll see the next question. Yeah, so this one. Okay, let me crop it. Okay, so yeah, we have given H is a subgroup of order P, where P is prime, of a finite group G, such that P is square greater than order of G. We have to prove that H is the only subgroup of G of order P, and hence it is normal in G. Okay, this is an interesting question. Okay, solution. So how do you approach it? Okay, given that H is a subgroup of order P. Okay, we have to show that H is the only subgroup of G of order P. Let there is another subgroup, say K of G of order P. Hence H intersection K is equals to identity. Why? Since H intersection K is a subgroup of H, also subgroup of K. So by Lagrange's theorem, order of this divides order of this as well as order of K. So order of H intersection K divides GCD of this one. Okay. Okay, fine. And we know order of HK equals to order of H, order of K by order of H intersection K, which is nothing but P and 1, that is P square. Fine. And which is greater than order of G we have given. Which is the contradiction? Why? Since, okay, let me write it clearly. Alright. Which is a contradiction? Because HK is a proper subset of G. So our claim, okay, so our supposition is wrong. So thus H is the only subgroup of order P of G, and since P square greater than order of G, we conclude that P square does not divide order of G. Okay. Thus, by Sylows theorem, H is a Sylow P subgroup of G, which implies H is normal in G. Why? Because this is also an well-known theorem that if a Sylow subgroup is unique, that is here H is the only Sylow subgroup, and which is Sylow subgroup, so it should be normal. Okay, so this is the proof.